September 12th, 2008. A hurricane named Ike is headed toward the beaches of Galveston Island in Texas. The eye of the storm, where the most intense winds are, is still hundreds of miles away. Yet the rising water has already spread over much of the island. 8 days back, researchers had flown into Ike and measured its winds at 145 miles per hour. That made it a Category 4 out of 5 on the Saffir-Simpson scale. Moving into the western Atlantic, Ike fed on a deep layer of warm ocean water, sweeping it up and growing to deadly intensity. Over 1 million people were evacuated from coastlines in Cuba as the storm approached. Ike weakened as it passed over the island. But as it entered the Gulf of Mexico by late September 10th, now on a beeline for Texas, it had begun to re-intensify. Residents of Galveston were ordered to evacuate. Most of the 58,000 residents did. But thousands remained to brave the storm. Despite the memory of another storm, over a century ago, that showed how vulnerable this low-lying island can be. September 6th, 1900. Powerful waves began lashing the coastlines of Louisiana and Mississippi. With swells rising in Galveston on the 7th, a hurricane warning was put into effect. That afternoon, a ship sailing from New Orleans encountered the storm. The captain estimated winds at 100 miles per hour, but at this point, little was known about the storm, where it would hit, or how bad it would be. By 5 p.m., hurricane-force winds began to pound the beaches of Galveston. By the time the hurricane came ashore that evening, its winds had risen to 135 miles per hour, a Category 4 by today's standards. Around 8,000 lives were lost in what remains to this day the deadliest natural disaster in American history. The city of Galveston was reduced to rubble by wind-driven waves and tides, called storm surge, over 15 feet high. The island had endured numerous storms since it was founded in 1838. What made this one so powerful? Hurricanes, also called cyclones or typhoons, are tropical storms that feed on solar heat captured by the oceans. When conditions are right, a hurricane can release this energy in a fury of wind and rain. A rare few, like the one that hit Galveston, go beyond the norm to marshal the extreme power of the seas and leave in their wake a legacy of devastation, death, and despair. One of the deadliest ever hit what's now Bangladesh in 1970. Moving ashore in a densely populated river delta, it claimed as many as 500,000 lives. In 1969, weather satellites launched earlier in the decade showed Hurricane Camille bearing down on the Mississippi coast. The storm intensified suddenly, with Category 5 winds of around 200 miles per hour and a storm surge that reached 24 feet high. Camille wrecked at the coastline, drowning 143. The storm carried huge amounts of moisture as it traveled inland. The result, when Camille hit the mountains in Virginia, was devastating floods that killed another 113. Then there was Andrew in 1992, in an otherwise slow hurricane season. Andrew accelerated into the Florida coastline with winds measured at 155 miles per hour. Andrew caused at least $26.5 billion in damage. Could it get any worse? Unfortunately, it did. These are photographs of the central, clear eye of Hurricane Katrina, taken by researchers who flew into the storm. From up here, you can see a beautiful architecture in the skies, built from clouds that erupt from the sea like a colossal bomb. Down below, wind-driven waves breached levees that had been built to protect New Orleans and flooded the city. The storm claimed 1,200 lives and inflicted an estimated $75 billion in damage. But for all the devastation they cause, hurricanes rarely surprise us today. A network of satellites orbits the Earth, sending down a wealth of revealing information about the oceans and atmosphere. Meteorologists tap into a network of buoys and ship reports to monitor ocean temperatures, wind, and wave heights, on the hunt for conditions that might be favorable for hurricane development. An Atlantic hurricane often begins its life over the mountains in East Africa, as an area of low pressure. It travels across the Sahara Desert, then moves out over warm ocean waters. Traveling with the trade winds that circle the globe just above and below the equator, these lows can spawn thunderstorms over a broad region. They gradually come under the influence of the Earth's rotation, called the Coriolis force, and begin to spin. Satellites orbiting the globe begin to peer into them to watch for signs of intensification. At the center, a region of low atmospheric pressure forms, known as the eye. It acts like a partial vacuum, causing winds at the sea surface to spiral inward toward it. These in-spiraling winds evaporate moisture from the warm ocean surface. As they near the eye, they rise rapidly, producing clouds and rain. Much of the air flows outward at the top of the storm, like a chimney. Some flows back down into the eye itself, causing this central zone to dry out and become clear. The path a hurricane takes is determined by its interaction with weather systems and global air currents. Scientists use supercomputers to try to predict not only where they will go, but also how they will behave along the way. Based on these predictions, alerts go out to shipping concerns, coastal businesses, governments, and the public at large. Over the years, meteorologists have improved their forecasts of the twists and turns of a hurricane's path. But at the same time, our exposure to these great storms keeps rising. From the coastlines of China, the Philippines, and Japan, to the Gulf of Mexico and the Bay of Bengal, coastal populations are growing faster than anywhere else in the world. Not only are there more people near the ocean, it takes more time to evacuate them all. Scientists have been computing the risks and running the probabilities of a terrible growing conflict between humans and nature. To reduce the margins of error, hurricane scientists will have to improve their ability to predict a storm's intensity as it makes its way toward land, whether it will fizzle, bringing only wind and high surf, or become a destructive monster. As large as a hurricane is, its behavior is subject to subtle shifts in wind and ocean currents, the presence of land masses, and the interaction of all the clouds and water molecules, and even dust entrained within it. Scientists are zeroing in on a few key diagnostics to predict when and where a storm might intensify and threaten human lives and property. One of them is the warmth of the ocean out ahead of the storm, the fuel that hurricanes thrive upon. Because hurricanes can draw huge volumes of water up from the deep, this warm surface layer must be thick for the storm to reach high intensity. When Hurricane Katrina, for example, entered the Gulf of Mexico in 2005, it encountered a wide and deep tongue of exceptionally warm water that originates in the Caribbean, called the Loop Current. As Katrina moved over this current, its winds picked up speed, reaching 175 miles per hour, Category 5 status. At the same time, a series of individual storms literally exploded within the main storm. You can see them in this sequence of satellite images. This often happens when the eye of the storm, the central region, contracts, getting smaller. The winds moving around the eye accelerate. Eddies or vortices begin to develop. These vortices cause huge amounts of moisture to evaporate from the ocean surface. Rapidly growing clouds then expand and shoot to the top of the hurricane. A computer simulation recreates the flow within these convective towers. As air from the surface accelerates upward, it pulls more air up from behind it. Because these clouds can be spotted as they first develop, they're a sign that things could really be heating up. In Katrina, the growth of these so-called hot towers coincided with its rise to super hurricane status. It also coincided with a fierce battle that had begun to develop deep within the storm itself. In this satellite image, a microwave beam was used to slice through Katrina at the point of maximum intensity. Convection had intensified not just around the eye, but further out as well. In radar images of large hurricanes and typhoons, scientists have been noticing a pattern like this since the early 1980s. Even as the eye wall forms, conditions are often so favorable for hurricane development that a second eye wall begins to form around it. The larger eye wall sweeps up moisture from the sea, fueling a new set of towers and sending clouds spiraling out the top. From there, the outer eye contracts and takes its place. This cycle helps explain Katrina's behavior on the way to New Orleans. In this radar image, Katrina is churning through the loop current as winds race around its relatively small eye. While the central eye wall remains intact, its energy is sapped by storm development on the periphery. And as it enters cooler waters along the coast, it ramps down to a Category 3. Unfortunately, hurricane behavior is never a simple matter. In 2008, with Hurricane Faye fading away, Gustav formed in the Caribbean and made its way toward the Gulf. It strengthened to a Category 4 as it approached Cuba. And up ahead lay the warm waters of the Loop Current. But as the storm approached Louisiana, cooler coastal water brought Gustav down to a Category 2. And it hit a relatively unpopulated stretch of coast to the west of New Orleans. With the memory of Katrina still fresh, authorities have been forced to empty New Orleans out in what became the largest evacuation in U.S. history. Ike was the next storm to blast across the Atlantic, developing 140-mile-an-hour winds on September 4th. 4 days later, its winds died down to below 100 miles per hour as it hit Cuba. Once again, the Loop Current loomed. Now, out in the Gulf, a series of convective towers shot high into the atmosphere. An outer eye began to form. As researchers flew through the storm, they wondered whether the outer eye would steal Ike's thunder, or contract in enough time to bring devastating winds to Galveston. Neither happened. The inner eye fought back and stayed just long enough to move ashore in Texas. As a result, Ike's eye and its energy were spread over a wide area. Because it bashed into a well-populated stretch of coastline, Ike became the third most destructive hurricane in U.S. history. The tools scientists are now using to study and predict the behavior of hurricanes are more varied than ever. Rainfall rates, lightning strikes, convective towers, the battle of the eye walls. These factors evolve with changing conditions in the storm environment. It's not surprising, then, that the more we learn about how hurricanes work, the more complicated this environment seems to become. Meanwhile, with each hurricane season, the population crowds ever closer to the shores. The stakes involved in understanding how, when, and where a super hurricane will form are rising ever higher.